Sorry,
Hani,
yes, it's just to keep the different lessons in separate videos. That is what the technician asked me. So I had to stop Hani video and start yours from scratch. Okay, sorry about it.
no, no worries, no worries. So Hani gave a very nice high-level overview. It was a little bit like flying in a jet plane at 40,000 feet, and I'll fly at a much lower altitude. So I will try to basically teach you elementary things, and you know, if you're already an expert or semi-expert, then you're welcome to go take a nap. I'll try and go at a speed where you should be able to take notes, which I think is always helpful to be able to remember anything afterwards, especially if it's a Zoom lecture. For part of the lecture, I will write on my screen, which is down here. So I apologize that there will be phases when I'll basically look down there and not directly into the camera, but we'll be able to deal with that. Hani mentioned that our material is in part based on a very nice review that just recently came out. Alexandre Blais is the first author of that, and you see the reference here. And so this chapter on the transmon qubit is close to section 2D in there. And then I also collected a couple of sources that might be interesting for reading. If you're new to superconductivity, I would recommend the chapter in the Feynman lecture notes. There's the transmon paper if you want to know all the details about that. I have a feeling that I won't get to go into the full details of circuit quantization just because of time, but there's a very nice paper by Michel de Boré, and you can access that. And then during the lecture, I will try, let's see how this goes, I will try and do some of the demonstrations and looking at qubit spectra with this SE Qubits Python package, which you can download and install on your own machine. Yeah, let's see how this goes. Oh, and last but not least, I should probably paste this in the chat. 1 second, where's my chat window? Over here. There we go. So there's a link to a website that is going to allow us to do polling. I will ask you 1 or 2 questions in between, just so that those of you who want to follow have a little bit more engagement. All right. Now, we heard from Hani that you know, you can build a harmonic oscillator out of a inductor and a capacitor. And well, our goal is to use superconducting circuits, not just as oscillators, right? Those might be interesting in themselves, but we want to use these superconducting circuits as qubits. And by qubits, I roughly just mean 2-level systems, except for perhaps the system, in fact, all of those that we will encounter have more than 2 levels. So there are levels above. And we'll try and make sure that we stay in this subspace. This is the qubit subspace. And in most situations, these 2 levels will indeed be the ground state and the first excited state of our many-level system. All right. So let's see. Hani talked about this LC oscillator, and I'll go through it briefly once again. So this Hamiltonian is simple. It consists of 2 terms, right? There's a charging energy term. You recognize that there's the charge Q. It gets squared and divided by twice the capacitance. And then the additional term here is the energy associated with the flux phi threading this inductor with inductance L. And so indeed, Hani showed that these two quantities become non-commuting operators. This phi, the flux, is basically our position, our generalized coordinate. And then this q, the charge, is actually our generalized momentum. And this indeed then looks just like a harmonic oscillator. And if you go through the same steps as you would for a mechanical one, you get the usual form written now in terms of the number operator A dagger A. And you get a spectrum inside this parabolic potential that is perfectly equidistant, right? Every spacing here is omega. And if we want to use this as a qubit, there's a little problem, right? So all circuits that just consist of only L's, inductances or inductors, and C's, they're all perfectly linear, by which I really mean that at the end of the day, they're just coupled harmonic oscillators, right? If I only have a single L and C, it's one. So let's rate oscillator. If it's more, then it's multiple ones, right? And together with a classical drive that I might try and use to excite this object, we see that there is a problem, right? So I might send in a tone that has the right frequency to lift our harmonic oscillator from the ground state to the first excited state. So here's my pulse, it arrives. But then once I'm in the first excited state, I realize that, well, there's a perfect frequency match for the first excited state to transition further upwards. And so we are not easily able to contain our system in the 0-1 subspace. And that has everything to do with these energy levels being equidistant. And well, that's what harmonic oscillators do. And so the question is, what solved this problem? And of course, Hanhi already mentioned the actual solution. The solution is that we will make use of Josephson junctions. And so Josephson effect was discovered by Brian Josephson a long time ago. And I'll keep this very, very simple. So the setting here is that of two superconductors facing each other. So the S stands for superconductor and the I for insulator. Right, so there's a barrier between those two sides. Classically, we would say that no charge can go through that barrier, but since there's tunneling, the charges, which in this case are actually Cooper pairs, they can tunnel. And as you may know, and if you don't, please do read a little bit in the Feynman lecture notes, which are beautiful. Every superconductor is described by a microscopic wave function for all the Cooper pairs together. And this wave function has a phase. So there's a phase phi1 associated with the left superconductor and the phase phi2 associated with the right-hand side. And so let's see, Hanhi gave me a nice image of an actual Josephson junction. So you see that there's one strip of aluminum metal that is down on the bottom, and then there's one on the top. And if you try to get this into a 3D image, then it might look like this. So the Josephson junction is the square patch over here. And what takes place as you fabricate this, very roughly speaking, is that you use E-beam lithography to put down the first bottom strip of aluminum. You let the aluminum oxidize so that the thin oxide layer, which is our insulator, forms. And then in the second step, you put another strip of aluminum on top. And so it's in this region here that you'll find your Josephson junction. How does the Josephson effect help? So to understand that, it'll be good to record the two central relations that we learned from Josephson. And the first one is called the current phase relation. It says that I may have a current flowing from one side to the other. And that current has a maximum strength. That's the critical current IC. And the phase difference phi is what governs the magnitude of the actual supercurrent. So if we call the difference phi1 minus phi2 just this phi, then the supercurrent is IC, critical current times sine phi. The second relation is the phase evolution equation. So this phase difference may change as a function of time. And what makes it change? Well, in our case, it's going to be primarily the voltage that I may establish between the two sides. So the voltage across is going to be V. And then for this to make any sense, there's some constants that need to go out front. So it's the Cooper pair charge 2e divided by h bar. So dimension, in terms of dimensions, this is correct now. And we can rephrase that just a little bit. So some of you may already know that h over 2e is that has dimensions of flux, and that is the magnetic flux quantum. And so we'll encounter that quantity multiple times throughout. And if I make use of it, then this expression can be rewritten as 2 pi divided by the flux quantum times the voltage. All right. Those are the two Josephson relations, and we'll see in a moment why this helps and in what sense it introduces nonlinear behavior. But I thought to make sure that everybody is still awake, we will try this polling game. So if you're already on that website, you should be able to see that you can enter an answer A, B, C, D, or unsure. And so here's my question to you. We're looking for a statement among A through C that is incorrect. A says for vanishing voltage across the junction, a constant current may flow. B says for a phase difference of 0 or pi, there is no current flow. C says a constant voltage across the junction produces an AC current. And D says, well, actually all of the above are correct. And so if everything is working properly, you should already be putting in your answers. I'll leave this open for one more moment. Let's see whether I'm receiving any answers from you. Let's see, I probably have to refresh this website. 3 responses. Out of how many are we? Where's my little Zoom? 37. Can we up that number a little bit, or are there technical difficulties that are keeping you from participating? 6.
Can you go back to the questions, Jens, that we
Yes,
don't...
I can, of course. I can try and just put my browser on a different screen. 1 second. Let's do this. All right. All right, now we have 12. Last chance to play the game. And then I will check over here what our results look like. So this is what our results look like. There's a decent majority for D. Maybe not enough for in the US to beat a filibuster, but I'll take that. And D is indeed the correct answer. So all A, B, and C are right. It's a funny situation. You know, if you think about a conductor, then all of this is sort of upside down, but it is true. If the voltage is 0, there may still be a constant phase difference across the junction, and then a constant current will flow. If I plug in 0 or pi for phi, then, well, the sign is 0 there, so no current. And then C is interesting. You see if if there's a constant voltage difference, then phi will ramp up linearly. And if I plug a linearly changing function into the sign, well, then I just get an AC current as a result. Okay, good. So we're awake. That's great. Then let's continue. So here collected are again our 2 Josephson relations. And there's one quantity which is sort of present through all of superconducting circuits, and that's the generalized flux variable. So flux, if you remember from Faraday's law in terms of dimensions, right? Voltage is the time derivative of flux. So we can play this game in a somewhat more abstract way and say that we'll define a generalized flux, which may not have anything to do with an actual inductor, by just taking a time integral of whatever voltage V is of interest to us. And if we do this for a Josephson junction, then, well, the result is the following. So we said that d phi by dt, don't actually need an equal sign here. So I can rewrite the voltage in terms of d phi by dt, right? And that allows me to write this as phi naught, the flux quantum divided by 2 pi, integral over time of phi dot of t prime. And that means that our generalized flux variable is directly related to the phase difference across the junction just by a constant prefactor. And that prefactor is the magnetic flux quantum divided by 2 pi. All right, so we'll make use of that over and over again. And the next question is, what is the energy associated with a Josephson junction? Where perhaps to make this clear, what this question is supposed to mean, we can derive what the energy is that is associated with an inductor, right? We already had it on a slide earlier, but to go through the motions, right, I would start by writing that the current is related to magnetic flux by dividing it through the inductance of the inductor. And then here, the flux and the voltage are really related by Faraday's law. There's no reason for me to worry about the sign here. So I'll just write that as phi dot equals V. And then the energy, right, you can calculate, and you have in some intro physics class, right? You would say that I take the time integral of the electric power, and power is just as good as I times V, right? Current times voltage. And you plug everything in, you get some intermediate result that says, well, it's 1 over L time integral over phi times phi dot. And that indeed gives you the ordinary phi squared divided by 2L. So that's the energy associated with an inductor, nothing new. And we can certainly do the same for our Josephson junction. And I think I put it here. Yeah, so those are the steps. Again, we plug in for P what we know about V and I. It's a simple integral that now involves a sign instead of just phi. That's our nonlinearity. And so the energy is given by a prefactor, which we'll generally abbreviate by EJ. It has units of energy and is called the Josephson energy. There we go. Times cosine, and the quantity that you have in the argument is really just the lowercase phi, right? That's the phase difference across the junction. Good. No questions so far? I don't see any. All right. Then let's proceed. So here again is our good old friend DLC oscillator. And the plan is that we now substitute this junction, inductor with inductance L by a Josephson junction. So here it is. Again, it might be something as simple as the aluminum oxide junction that we saw in the pretty picture from the IBM group. And what does that do to our Hamiltonian? Well, nothing changes about the capacitive energy, right? That's, again, Q squared divided by 2C. But now the energy of the inductor gets replaced by the energy associated with the Josephson junction. And the potential that I plotted over here was our parabolic potential of our generalized coordinate phi. And I can plot something similar over here. Now our potential energy is actually a cosine rather than a parabola. And well, what happens as a consequence of that is we will see that the energy levels are now not equally spaced anymore. They actually decrease, the energy differences decrease as you climb the ladder up to a certain point, which is precisely what we wanted if we were interested in using such a system as a qubit. All right, and then the standard form to rewrite this Hamiltonian is indeed to recognize again that this quantity is the lowercase phi, our superconducting phase difference, and then the first term is oftentimes rewritten in terms of the dimensionless charge operator. So this n operator is q divided by the Cooper pair charge, q divided by 2e. So this counts the number of Cooper pairs, and then this gets multiplied by 4 times the charging energy. The 4 is just a convention because people historically decided that they wanted to write this as the charging energy of a single electron rather than a Cooper pair. All right, and here's what such a device might actually look like. It's very, very simple. You have 2 big superconducting pads of metal, and they're connected here by a thin wire, and that thin wire in the middle is interrupted by a Josephson junction. This one looks a little bit different from the one that we saw earlier, but the concept is the same. And again, the circuit is this. You have a big shunting capacitor, which is, these 2 pads act as our 2 capacitor plates, and then they are shunted by this Josephson junction. Good. Now, before we dive a little bit more into how do we actually get these energy levels, what do wave functions look like, it's good to get a little bit away from this very abstract form with operators and hats on top, and to go into what I might call position representation, right? This phi is what I imagine to be the position of my fictitious particle described by this Hamiltonian. So phi is the position, and then the momentum gets replaced by I d by d phi. Since things are dimensionless here, there's no h bar that pops up, and you can check that this is indeed the correct way to write this. So now we have our Hamiltonian sort of as a differential operator. That's great. And then, of course, we stick this operator into the Schrödinger equation. I've done that. Question is, do we need more, or can we just obtain the energy levels now that we have this equation? So my question to you is, what about boundary conditions? A says, well, they're just the usual ones, namely, if our position variable grows large in magnitude, then the wave function must vanish sufficiently quickly so that wave functions are normalizable. B says boundary conditions are only for the weak. We don't need them. Who cares? C says the wave function must vanish at plus pi and minus pi. You see here they are. And D says none of the above are the correct answer. And I think before you vote, I have to reset my little poll. Otherwise, we'll get funny results. Clear. Okay. So I hope that you're able to vote now again, just using the same poll. Is that does that work? Has anybody started doing this? Let's see. Yep, 3 people have been successful. I'll wait for another moment. 9. Okay, can we get 13? I like 13. It's a nice number. It's still a small fraction out of the people here. 16. All right, I'll take that. So let's see what our results show. And this is what the results look like. That's pretty evenly split between A, C, and D. Nobody liked B. Boundary conditions are for the weak. Nobody believes that. Okay, well, I like to hear that. D is the correct answer. So A, our potential is purely periodic. It's not confining. So there's no reason why the wave function would want to or need to go to 0. When we go far out, the potential would keep oscillating. Option C would be the right option if I had an infinite square well with walls at minus pi and plus pi, and I don't. So neither of those 2 offers for boundary conditions are correct. The correct choice is the following. Let's see whether I can go forward. Yeah. What is the meaning of this phi? Well, it's the phase difference across the junction. For this phase difference across the junction, is there anything different between 0 and 2 pi? And the answer is in this circuit, without any inductance, right, there isn't. Those 2 points basically correspond to the same point in space. If you want to imagine this as a fictitious particle living in some potential, then this particle actually lives on a circle. So the boundary condition is that whenever I add 2 pi to my position argument, then the wave function just has to repeat. So it's periodic boundary conditions. And that, by the way, and I will not show that formally, but it's not hard to figure this out. This periodicity of the wave function is directly related to the fact that this n, that counts the number of Cooper pairs that we have on either the upper piece of our circuit or the lower piece, that n operator has a discrete spectrum. It counts Cooper pairs, and since only full Cooper pairs can hop across the junction, I will never find a fractional Cooper pair, except later on when we think about quasi-particles, but that's a separate topic. All right, and then let's actually take a look and see those energy levels and wave functions for concrete parameters. So this is now the dangerous part of the lecture, where we'll see whether I can do a little bit of coding in real time. So what do we want? We'll import this SE qubits package that you can install if you want to. So we'll import it, and then we'll just call the simple graphical user interface. There's my first typo, SEQ. And let's hope this works. So it brings up this view graph. You see there's a bunch of superconducting qubits. We're interested in transpon that's active, and we'll look at wave functions. And so here's the plot. You see the cosine potential, right? And you see the lowest lying wave functions, ground state, first excited state, and so on. And as you're used to from textbooks, these wave functions are offset such that they're centered wherever the whatever the corresponding eigenenergy is. And down here, it looks pretty equidistant. We can change parameters a little bit and make this more extreme, perhaps. Let's see. Yeah. All right. So now I've changed parameters a little bit. There's basically 2 that we can play with right now. Haven't introduced the others. There's EJ, the Josephson energy. There's EC, the charging energy. And in this example, you should see now that this distance, the energy difference between ground state, first excited state, is certainly larger than, well, definitely this one. And in fact, it's also larger than the other 2. All right. So that's sort of a quick overview of wave functions. Interestingly, when I asked for a couple more, let's make them up there. You see that they live, those wave functions live above the cosine well. They're also properly periodic. And we'll talk a little bit more about them later on. But for now, I just want you to appreciate that there are wave functions above the top of the cosine hill. And their nature is somewhat different from the ones that are sort of semi-bound to this cosine potential. Okay, I think that's what I wanted to say on this note. So let's see, timing. I have 4 minutes if I don't want to go over time. So we'll start with the next section and then probably have to pause. So I've shown you the circuit. You've learned a little bit about its spectrum. Hanhi has given it a lot of praise, and well, it's true that it's widely used, but is it a good qubit? And in fact, what makes a qubit a good qubit? And why is making good qubits difficult? Because took us quite a while to get from very small coherence times to the ones that Hanhi advertised, right? Transpon 2007, that's many years ago. So let's talk a little bit about that. And the story is that in qubits, there's a natural tension between 2 things that you need to achieve. One is your qubit is never alone in the world, right? There's an environment, a physical environment that the qubit might interact with to some degree, and interact with in an uncontrolled way. And whenever that happens, the qubit will lose information. Decoherence takes place. That is sort of the umbrella word for loss of quantumness. And so a good qubit must be nicely protected from the environment. On the other hand, we really want to do stuff with our qubit, right? We want to be able to manipulate its state, and we want to be able to read out the state in the end. And that means that we must have good access to this object so that we can do state manipulation and readout. And those two things are, that there's a great tension between those two. Giving you just one example, you know, what if I had a qubit that was really nicely protected from the environment? What would come to mind? Neutrinos might come to mind, right? They are nice quantum systems, but they basically don't interact with anything. That means they're protected from the environment, but they're also protected from me. I can't do operations on neutrinos. Very, very hard. I don't think anybody knows how you would try and do that. It's probably not possible, right? And so we must find a compromise between these two sides, and that is what makes developing and fabricating good qubits so difficult. So I already said decoherence is just this umbrella word for loss of quantumness. That's at least the way that I use this word. And then when you split it farther apart, there are two important decoherence mechanisms. There's one that is called depolarization, and there's another that is called pure dephasing. And I might be able to get started with that, but probably have to pause there in just a moment. So we said the qubit, our two-level system, is not alone in the world. Indeed, there are a lot of processes that we've learned about and that we know of today that are unwanted, and they influence the qubit and lead to decoherence. I don't think that in the course of the summer school we'll really be able to cover all of those in real detail, but Hanhi already mentioned charge noise. There are other types of noise, flux noise, the critical current of the junction might fluctuate. Dielectric loss is very important, as Hanhi pointed out, and then there are other noise channels as well. And as a consequence of that, there is decoherence. You know, if you imagine you had a quantum computer, then that leads to errors. And if your quantum computer has an operating system that looks anything like Windows, right, then you'll get this error message. Your qubit ran into a problem that it couldn't handle, and now it needs to restart. And that's terrible, of course. And if that happens too often, then there's nothing that you can do with your quantum computer at all. And so we'll have to talk about what depolarization and pure dephasing are, how we understand them, and in what ways we can actually mitigate those errors and come to a place where we actually have a nice compromise between these two sides of isolating the qubit and having good control over the qubit. Good. I think this is an okay place to pause. I had meant to get a little bit further, but I'll make up for it in the next lecture and be happy to answer any questions that you might have.
Thanks, yes, that was a great lecture. Let's see if there are questions.
Somebody raised their hand. Leonardo.
Yeah, so thank you for your very nice lecture. So my question has to do with potential noise sources. For example, there exist some models of dark matter, which could imply that there is some interaction with certain atomic states. So has there been have there been studies that have been looking for example, modulations in potential noise in these systems? For example, if there was a dark matter particle interacting with such a system, then we would expect there to be yearly modulations, even daily modulations. So has there been any interest in that?
There has been interest. I think Katerina is actually the perfect person to answer that question. Alexandra will say a little bit about what can contribute to trying to measure such things. And my understanding is that Katerina will talk about that in much more detail. The objects that people think about using for detection are not actually the transpond qubits. That they would be helpful in such a protocol, but it's actually a simple cavity that would play the main role in some of these schemes, I believe. For transmons, I think it's difficult in that, you know, as long as there's other noise sources like the ones we know of that dominate, it'll be really hard to see the little effect that something as subtle as dark matter presence might have. You'll be looking at a teeny tiny noise signal on the top of a huge amount of noise. So I think I imagine that being difficult, and understand that for cavities the situation is much more promising, because cavities they don't care about charge noise. To some degree, they don't care about flux noise. There's no critical current noise. There may be some dielectric loss, but Fermilab has been fantastic in optimizing that. And so that system is much simpler and much cleaner.
I see. Thank you.
And Katerina, you can jump in to add on if you like.
Well, you correctly answered. The core here is the cavity. The cavity has a role in those dark matter experiments, because in the cavity there's, if you talk about the axions, we get a conversion. So it's mainly related to the cavity parameters, the efficiency of, let us call it the efficiency of this process of conversion, and the qubit in perspective acts as a photon counter. So you count the photons that are generated in the cavity by the dark matter particle interaction, and these devices can play a role in the sense that they can really enhance the speed of the search. So, but yeah, we will see that in the quantum sensing lessons, but mainly in Alexander also lessons.
Right, thank you very much.
Julia?
Yes, thanks. May I ask you a question about kind of charge and flux noise? I know what lots of microscopic models. Do you have some kind of preference or believing in some stuff which could really kind of well explained it? It's just maybe a bit more philosophical question, but I'm curious about your opinion on that topic.
No, I think it's not a philosophical question. I think it has, in some places it seems like it has become one, because it's been difficult to actually verify some of the models that have been suggested. I don't think I have a preference. I think there have been some good indications by through experiments in Robert McDermott's group that perhaps oxygen spins on surfaces have something to do with flux noise, but whether that's really all of it, I don't know. In many cases, people just mumble, there's two-level systems, and if you have the right distributions in kind of their energy splittings as well as tunnel rates, then you can cook up something that looks more or less like 1/f noise. But I think there's no clarity right now on the real microscopic models in great detail.
Okay, so your opinion that we need a kind of a nice experiment just to prove at least one of the model.
Yeah, I think that would be very interesting. It would be a big step, because I imagine that with a microscopic detailed model, you really understand the origin of the noise so well that you might also know how to make the noise itself less severe, right? One of the games that we've been playing in this field is we sort of say that making the noise less significant is a hard material science problem. We may not know how to do that. What we can do more easily is to adjust our circuit in such a way that it is not sensitive to the noise channels that we know of. And so that's a fun game to play, but it's also a game of avoidance, right? If you figure out what really produces all that charge noise, and as a consequence of that, have an idea how to make it smaller, lower the amplitude of that noise, that would be fantastic.
Thanks.